Abusing insecure WCF Endpoints. Fabius Artrel nos mostrará distintas herramientas y técnicas para identificar endpoints inseguros en el Windows Communication Foundation, cómo explorarlos y cómo el ataque sobre estos afecta a la seguridad de software real.
Okay. Can you guys hear me fine? See? All right. Hello, Ekoparty, and thank you for coming to my presentation on abusing insecure WCF endpoints. So my name is Fabius Watson. I work for a security firm out of Atlanta in the US called Versprite as the security research manager. My interests include reverse engineering, exploit dev, vuln research, and post-exploitation. Before working as a security researcher, I worked as a SOC analyst, and I have a handful of certifications, as you can see, that certify me as a hacker. So an agenda of this presentation, first I'm going to go over a high-level overview of WCF, primarily what relates to attacking it, none of the really low-level underlying stuff. After that, I'm going to explore WCF target enumeration, how to find which applications use this technology. Then I'll go over analyzing WCF applications in order to identify potentially vulnerable endpoints. I'll go over abuse cases and real-world software so that you can see it's not just an experimental vulnerability class. And then associated with those real-world vulnerabilities, I'll go over some demos of exploiting insecure WCF services. So the motivation behind this research, Versprite was doing some Windows VPN software auditing, and we noticed that a lot of the Windows VPN software had .NET services. We also noticed the trend that tons of these services were exposing methods using WCF, and most of these services were also running as local system, which is the highest privilege level on Windows operating system. So we investigated the possibility of abusing these endpoints in order to execute the privileged methods that were exposed. So what is WCF? So WCF stands for Windows Communication Foundation. It was originally called Project Indigo by Microsoft in the year of 2000, which shows that it's been around for quite a long time. And it's basically a set of APIs that allow the communication from a client to service to be very simple. It supports a handful of protocols, TCP, HTTP, and you can also build your own custom protocol to work with WCF. So Microsoft tried to make it very inclusive. And to make it simple, WCF clients connect to WCF services, and WCF services perform operations on behalf of the clients. So right now I'm going to talk about the ABC of WCF. This is the core of communicating to an endpoint. So make sure to keep this in mind, and I'll go over it again throughout this presentation. So the A of the ABC is address, the B is binding, and the C is contract. The address is just the endpoint's URI that represents the location of the endpoint. Here's an example that I got from Microsoft, and the address has 4 parts. It has a scheme, the machine name, the port number, and the port number is optional depending if the binding that you choose supports port numbers. And finally, the path. In this case, it's math_service.svc because the Microsoft example was a WCF service that supported math functionality. The B of ABC is the binding. The binding determines which protocol you're using, the encoding scheme, as well as any transport security that you enable. Here's a list of the system-provided bindings. As you can see, there's a lot of different bindings, and as I mentioned before, you can create your own binding. And finally, the C, which is probably the most important from the perspective of analysis, is the contract, which defines the service and operations exposed by an endpoint. So the service contract in the code is identifiable by the service contract attribute and the operations by the operation contract attribute. And here you can see that the service name is my contract and the operation exposed is populate data. So now that I've talked about the high levels of the ABC of WCF, I'll talk about enumerating targets for analysis. So whenever you're looking for a local WCF target, you want to find a .NET service that runs as a local system because that would gain you the most privileges if exploited. The first way that we went about finding .NET services that run as local system is using sc.exe, which is used to gain information about services. So we ran a sc query, which gives a list of all the services, and after we got a list of services, we chose a service name and ran scqc plus a service name to get the user that the service is started as well as the binary path name. As you saw, this way doesn't always work well. It takes a long time to guess which service you want to look at. So we found a more efficient way. Using WMIC, we're able to query for all running services that run as local system. And we were also able to filter out servicehost.exe because we know that this isn't built with .NET, so it's not within our scope of targets. And this returned only 6 services. It returns them very quickly, which speeds up the process of identifying a target service. However, this still doesn't confirm that they're built with .NET, only that they're running as local system. Next, we took the fact that .NET applications have the dependency of mscoree.dll. So our approach was to search for this string within the binary application using WMIC, find string, and for loop, all native to the Windows command prompt in order to only find the services that are running as local system and include this string. This returned only this value, vuln WCF service, which will be our target upcoming throughout this presentation. However, this is still liable to return false positives because it's just a string search. It doesn't really check to see that it's imported. Finally, we wrote a Python script that uses PE-file, which is an open source library for Python that allows you to gain information about PE executable. And we checked the import table for mscoree.dll. Here's the snippet of the code that actually does this. It just iterates through the list of imports and matches it and prints out the binary path name. And this way was the most reliable way that we found in order to find .NET services that start as local system. Now, outside of that, you can also use a graphical tool, Process Explorer from sysinternals, and there's an option called Configure Color. You can configure Process Explorer to show .NET applications and services with the yellow background. So as you can see here, we ran it and vuln WCF service has a yellow background. We can also see that it's running as NC Authority system, and usually if a .NET application is running as a system, then it's a .NET, or it's a .NET service rather than just a normal application. Outside of searching locally, of course, most people want to find other targets online that they can potentially attack. I'm going to go through a few of the methods that we use. They start off pretty bad. Iteratively, they get a little bit better. Not saying any of these are the best ways, but these are the ways that we've gone about finding remote targets. First one is to search for applications that are similar to ones you know use WCF. When we did our audit of VPN applications, we found one that had a vulnerability in WCF. Then we looked at other VPN applications and saw that they were doing the same thing. So if you look at similar applications, then you're likely to find similar vulnerabilities. The next thing we did was search for .NET Service or .NET Agent on Google. We also looked for .NET Installer and installed the application and saw if any of the services existed that used WCF. This approach wasn't great, but it was fruitful in finding at least one vulnerable application. Finally, the most recent approach is to look at WCF error messages and finding online people referencing the error message in an application name. And that will give you the information that, hey, this application uses WCF, let me take a look at it. As you can see here, there's an error message called endpoint not found, which is associated to an application being unable to reach a WCF service. We searched for this particular error message. We filtered out Stack Overflow and Microsoft.com because those were primarily showing examples of people trying to develop using this technology. And the results are 222,000 results. And using this technique, we're able to find quickly several applications that use vulnerable WCF endpoints. So now that we've talked about how to find the target, I'm going to talk about how to analyze Vuln WCF service, which is the service that we found. So Vuln WCF service is a service that we developed to demonstrate the analysis and exploitation of abusing WCF endpoints. It can be found here on GitHub at Versprite's GitHub repository. And its implementation is modeled after the different code bases that we analyzed that use WCF technology. So we begin our analysis with decompiling Vuln WCF service. We use dnspy to do this. And dnspy is an open source debugger, assembly editor, and decompiler for .NET that makes things super simple. First, we want to look at the references node. References are basically dependencies within .NET applications. The most important reference for the sake of WCF is system.service model, because that contains all the types and all of the classes necessary to use WCF. If a .NET service doesn't include this reference, and none of its references includes a reference to system.service model, it doesn't use WCF, so you can save time by moving on to the next application. Next, we're going to talk about the other nodes. The first one is the namespace node. It's yellow, and on the left-hand side, you have curly braces. Following that, you have the interface iVuln service. All of the interfaces in .NET start with the capital letter I, which is something to look out for if you're looking for a service contract, because they're often implemented as interfaces. We have vuln service, which actually implements iVuln service. And then we have the main method, which is vuln WCF service, which will include all of the service creation code. So the service contract is defined in iVuln service, the interface that we just mentioned. You can see it has a service contract attribute, and you can see it also has an operation contract attribute over the method named runMe. So vuln service actually implements that interface. You can see that runMe is just defined as a function that takes in a string, writes the string to the command line, and then starts a process using that string as part of the command line argument. And it runs it using process.start. This is a simple runMe as it clearly defined, and although it's a contrived example, we saw things like this in the software that we audited. The main class starts off by using system.service model and system.service process. System.service process is used to create services in .NET. The service is defined as vuln WCF service, as we saw whenever we were enumerating the target. And the onStart method is what's called whenever a service is started. So within the onStart method, we have the base address. This is the address of the ABC of WCF. You can see that it has a scheme of net pipe, the machine name of localhost. It has no port number because pipes don't have port numbers. And it has a path of vuln service / runMe. We can also see that a service host instance is created using the contract and the address associated with this service. The contract is a vuln service, and the address is defined by the base address. And binding is defined as a net named pipe. That's an abstraction of named pipes used for WCF services. It's really quick, which is why a lot of people use it, because it's local to the system versus TCP or HTTP. Next, within the onStart method, we have a call to add service endpoint. This is one of the most important methods that you want to look for whenever you're analyzing WCF services, because it consumes the address, binding, and contract, the ABC, in order to deploy the endpoint. Following the call to add service endpoint, it calls open to actually start the WCF service. As I mentioned, make sure to look for this if you're analyzing any WCF services, because it's going to give you all the pieces you need to write a client for the service. Speaking of clients, I'm going to start talking about building a WCF client to connect to vuln WCF service. There are a handful of ways to create a client, but the biggest point is that you don't have to know a lot of C# in order to build a client, because a lot of the code can be auto-generated. So the first thing I want to talk about is leveraging proxy libraries. Legitimate WCF applications have a library that contains all of the service contracts and types necessary to connect to the service. So we can possibly, with our client, reference these pre-existing libraries in order to connect to the service without writing any new code. So basically, the developers of the target are giving us the code to use to connect to their service. And this greatly reduces the amount of time necessary to build a client because you're just using pre-existing types and functions. As you can see here, there's a service proxy.dll loaded into dinspy, and one of its references are system.service model, which indicates that it's a service proxy library. There's also a tool from Microsoft called svc util.exe. It consumes metadata in order to auto-generate the proxy code for you to use to connect to a service. The metadata comes from the WCF service if it's exposed, but that's not enabled by default. However, you can also use svc util.exe on the service binary in order to generate the metadata, and then use it again on that generated metadata in order to auto-generate the code necessary to connect to the target. So let's talk about building evil WCF client, which is what I've named the exploit client that we're going to develop. So it remains possible to build a client without a proxy library or metadata. All you need to do is use the information gained through static analysis in order to communicate to the target service. As I mentioned, very little C# is required. As you see, building a client will go by very quickly because Microsoft made it very simple to use their technology. So there's a few requirements in order to build a client. First, just like with the service, we have to use system.service model in order to use any of the WCF functions or methods. Also, if no proxy library is available, we have to include the service contract inside of our code ourselves. So you can see that we took the service contract from the decompilation in dinspy, we copy and pasted it into our client, and now we can reference that service contract within our code. And from my experience, copying and pasting from dinspy is, it works pretty much all of the time. There hasn't been any errors when I've used it, so that's less code to write. Next, we want to talk about WCF channels. Channels are how the client communicates to the service, and it does this through message objects, through the channel stack, which is the pipeline for communication. In order to communicate over the channel stack, we have to use a channel factory in order to generate a client to communicate to the target. And the channel factory also consumes the address, the binding, and the contract. This is why it's so important to find the reference to add service endpoint in order to get that information so that we can build a channel factory in order to communicate to it. As you can see here, we have a channel factory. It's using the type ivuln service. It has the address that we retrieved from dinspy, and it also is using a net named pipe binding. Whenever we call create channel on this channel factory, it returns a service channel proxy, which we can then use to call the methods that are exposed by the service. So here, we simply call channel factory.create channel, and it returns client, which is our service channel proxy. Then we call client.runme plus a string that gets appended to command.exe. And as a result, we look at vuln WCF service, and it has subprocesses of CMD and calc.exe, both of which are running as NT authority system. And that's it. It's very simple. Microsoft made it very simple so that people didn't have a lot of problems and use their technology. And we can also use their technology to exploit insecure endpoints. So now let's look at real software. Real world vulnerabilities. All right, so the first thing we're going to look at is CVE 2018-10169, which was a vulnerability in Proton VPN that allowed for privileged escalation to system. It established a service that communicated over a net name pipe, and it exposed the connect method, which allowed an attacker to control the OpenVPN config path. And with OpenVPN, there are a handful of options you can include in a configuration file. One of those options are plugin. And with the plugin option, you can define a DLL for OpenVPN to load whenever it's executed. And by using this feature in OpenVPN, we're able to create a client that allowed us to escalate privileges through the WCF service. So first, let's talk about the discovery of this vulnerability. So as I mentioned, we audited several Windows VPN clients, and we saw that Proton VPN offered a free limited subscription. Primarily, we were interested in starting off with free VPN clients because we didn't want to pay someone to audit their software. So after downloading this application and installing it, we ran SC query, which lists all of the services installed, and we filtered it down to only the ones that included Proton, which revealed Proton VPN service. We then ran SCQC, Proton VPN service, which revealed the binary path name and also that it starts as local system. So we proceeded with analyzing the application named Proton VPN service.exe. So we started off by decompiling it and looking at the references. We see here that it has a service proxy reference, which is a big indicator that it's probably using a service proxy library. We also see that it's using system.service model, which indicates that it is using WCF. So using a feature in dnspy called the analyzer, we were able to just find usages of our target function, which is add service endpoint. We find two instances of this method being used, one in service host.service settings, another one in service host.vpn connection manager. In the VPN connection manager proxy host factory, in its create function, we can analyze the call to add service endpoint. We instantly get the ABCs of this particular service. The address is netpipe localhost proton VPN service connection manager. The binding is a net name pipe binding, as is returned by build name pipe. And the contract is IVPN connection manager proxy. Given this information, we have enough to connect to the service, but we want to know what that connection will provide us. So if we analyze IVPN connection manager proxy, we can see that it's defined within the service proxy library that we saw earlier, and these are all the methods that are exposed. There's a callback contract in the service contract field. What this means is that there's a two-way communication that's expected, so we have to establish a duplex channel instead of a normal channel factory. We also see that the connect method takes in a service connection proxy argument. This makes it the most interesting method because only the disconnect method takes a Boolean value and the other methods are void methods. So we investigated how the connect method was implemented more closely. So the service connection proxy class is basically used to store information about the service connection. As you can see here, one of those values is OVPN config path, which we control if we control the object of type service connection proxy. And using, as I mentioned before, using this OVPN config path, we can create a new config file, reference it, and include the plugin option, which holds our malicious DLL that will do whatever we like. Because in DLLs on Windows, there's a DLL main section, which will execute whatever code's in that section whenever it's loaded. Even if it doesn't successfully reach the function that is targeted, it will execute whatever code we want whenever it's loaded. So to begin writing our exploit, first what we want to do is reference the proxy libraries that are existent within the Proton VPN service. So we add the reference in Visual Studio, and then we add using Proton VPN service proxy.vpn. This gives us all of the types and classes necessary in order to connect to the service. Next, we create the duplex channel factory. It's similar to the example I showed before. However, it also includes an instance context to the type that it needs to communicate, the callback type. However, you don't have to write a true callback function. What I did was I used Visual Studio to auto-generate a callback function that throws exceptions on each of the callbacks values and methods. So I didn't really have to write it. I just used Visual Studio to auto-generate a filler callback method. And the duplex channel factory, as I mentioned, it consumes the address, the binding, and the contract. And as I also mentioned, it uses a dummy implementation of VPN events callback. But as you can see, the ABC are all we really need in order to establish a connection to the target service. We call create channel, and it returns the service channel proxy that we named VPN client. So the DLL payload that I chose to use is called OpenVPN POC.dll. In DLL main, It just starts a bind shell on the system, listening on port 4444. Whenever anyone connects to it via netcat or some other terminal service, they are provided with a command prompt shell. So after adding the plugin option to the config file, I set the path of our DLL, the path of the config file to the OVPN config path variable within our service connection proxy that we created. And then I call connect on our server connection proxy to trigger the vulnerability. And instead of using netcat, I used the .NET TCP client class in order to actually connect back to the bind shell and gain our system shell. So here is a video demo of this in action. As you can see in the folder, I have ovpn_poc.dll. Also have service proxy, which came from Proton's VPN installation folder. Then I have the POC file. So first I run who am I. It returns IE user, showing that I'm unprivileged. Then I run the exploit. It runs, it creates a config.ovpn, which contains the plugin value. I run who am I again after I drop into the shell, and I have a system shell quickly because it's over a named pipe, which means that it'll be near instant in execution. Thank you. So the next target, or actually the next targets we looked at were other VPN services. We found similar vulnerabilities in NordVPN, Viper VPN, TunnelBear, and CyberGo6. All of these had similar WCF vulnerabilities because they were calling OpenVPN in different ways through an exposed insecure endpoint. The next target we're going to look at is Kiosk Simple. This is a vulnerability that an intern at Versprite actually found this past summer. So Kiosk Simple is a kiosk software that you install on Windows to turn it into a secure kiosk environment. So we found a privilege escalation vulnerability through WCF in Kiosk Simple because it exposed methods that allow you to read and write to the registry as well as control services. And we abuse these methods in order to escalate to system, and I'll show you how. So first, we started with analysis. We put it into dnspy, decompiled it, and we saw that it was obfuscated. Like, nothing had a proper name. 1, 2, 3, 4, that wasn't valuable to us. Luckily, the metadata included a hint. It said powered by Smart Assembly 6.11.1.354. So by Googling Smart Assembly deobfuscator, quickly revealed an open source tool called DE4dot, which we use to decompile the application. As you can see here, it saves the output to kiosk simple service -clean.exe. So after loading the clean binary into dnspy, it's a little bit more friendly. We used the analyzer again to look for add service endpoint and revealed that the method in namespace 0, class 0, method 0 of kiosk simple service calls add service endpoint. So analyzing the calls to this, again, revealed the address, binding, and service contract. The contract here is iRegistry service. The binding is a net named pipe binding. And the contract, the address is net.pipe localhost kiosk simple plus the pipe registry. So within the registry service contract, there are several methods, and some of them are particularly more interesting than others. Those are change local machine registry value, which immediately caught our attention, start service, and stop service. And knowing the functionality of these different methods based on their names, prior to even analyzing them, we got an idea of how we would exploit this particular service. So here's our attack plan. First, we want to populate the image path key of the target application using the change local machine registry value method. Services in Windows have a value in the registry called image path, which points to the application or the binary that will start whenever the service is started. So if we change this value, when the service is started, it will run whatever executable we define. After we change this value, we want to call stop service in case the service is already running. Then we want to call start service in order to cause the application that we chose to execute as system. What we noticed was the parameters to these methods, it was required that they were triple S encrypt it with a password and then base64 encode it, which at first we thought we were doomed that we couldn't exploit this because we didn't have the password. However, the password is actually hard-coded to the application, so it wasn't truly secure. It was like, I don't know, security theater, I suppose. So after referencing Kiosk Simple's cryptographic library, just as we did with the service proxy library, they had a cryptographic library that we just chose to use instead of implementing our own triple S encryptor. We just used their encryptor class in order to encrypt our argument values. As you can see, the service name is Razman. That's a service we targeted because it starts as local system and it's not super critical if it goes down or comes up. However, through this particular technique, we could also change the start name of any service to local system because we can change registry values. The target key is, the target name is image path, and the value that we want to change it to is netcat listener on port 4444 that starts theme.exe in order to keep it simple. We encrypt all of these strings using the super secure password of KS simple ENC pass and encode it using the encryptor. And then we use our service channel proxy called client in order to call change local machine registry value using some of these keys. After this, we'll stop the service and then start the service in order to execute our command as local system. And here's a demonstration of this. So as before, I'll run who am I in order to demonstrate that I am just a user, a low privilege user. We can see that the image path right now calls service host.exe. After we run the exploit, we get a shell inside of Windows System 32. We run who am I, and we're in the authority system. If we refresh the registry editor, we check the image path again. We see that it contains our netcat string. And if we go to Process Explorer, we can see our netcat client is connecting on 4444 as user, and our netcat service is listening on 4444 and it's running as NT authority system. And that's how we got our system shell through this particular exploit. Thanks. So the next thing I want to look at is Rce variants of these particular attacks, because so far we've only looked at local privilege escalation. Everyone knows that remote exploits are a lot sexier. So what we did was using the techniques that we discussed previously in finding a remote target, we discovered a service particularly looking for the error messages associated with WCF. We quickly discovered a service that uses, it establishes a remote WCF endpoint and listens on the, not just the local network, but on whatever system is able to access that target. And it's an application, popular commercial bandwidth performance and fault management application. Some of you guys might be able to guess what this application is, but we'll release more information later on the Rce Variants website as well as their Twitter. The service exposes an insecure remote endpoint through net TCP binding, which is a change up from our net named pipe binding that we've been using thus far. And I actually found this while preparing for Ekoparty. I was building the slide deck and I was like, man, this is lame. I only have local privilege escalation vulnerabilities. I need to find something remote. So I applied the techniques that I showed you guys, and I was able to find this vulnerability. And as I mentioned, you can follow @Versprite for release details. So analysis of this particular service, it exposes many WCF endpoints. Probably the most I've seen in any of the services that I've analyzed. There are tons of endpoints. The one that caught my attention was invoke action method. It takes an action ID, a method name, and arguments in order to actually execute a particular command. One of the action type IDs that I noticed was execute external program, which again caught my attention because surely this wasn't an endpoint that executed whatever program I told it to. However, analysis revealed that that was the case. However, we also noticed that it was a secure endpoint, supposedly, because it required a password, and I didn't have a password. However, the password wasn't a real password. It was a hash of the username. So again, almost security theater, and that's a trend that I've also noticed, people attempting to secure WCF services, but doing so improperly. And so in order to exploit this, It was very simple. It was essentially the vuln WCF service run me example, except a remote variant. So I decided to use a PowerShell one-liner that gives a reverse shell, adapted from the Nishang PowerShell library that you might be able to find on GitHub, and set up a listener that receives this reverse shell and gain a remote system shell. And here's a demonstration of that. This is a PowerShell prompt on the attacker machine, and I run hostname. You can see that it's a laptop. I run who am I? I'm at laptop/Fabius. I run the POC against the IP address of the VM that I tested this in. Establishes the connection, gets the identity, hashes the password, creates the channel, sends the command, waits for the connection. It takes a little bit, but it's worth it because whenever it actually does return, we're presented with a PowerShell system shell. I run hostname. You can see that the hostname is MSEdge Win10, which is our expected identity name. I run who am I, and I'm system. Thank you. As I mentioned, using the techniques described here, like analysis is quick because all you have to do is decompile it, search for @service endpoint, and identify the service, the implementation, find all the methods that are revealed, see if they're useful, and if they are, exploit them. So mitigations, it's important. So number one, avoid exposing any potentially dangerous operations. Don't expose operations that run code. Don't expose operations that modify critical system variables. Don't do any of those things because without doing that, even if you have the most insecure endpoint, they can't be abused. Next, make sure that you securely program any operations that you do expose. For instance, some of the exposed operations seemed benign, but the way that they were implemented, they had vulnerabilities in the actual implementation, such as command injection. Also require proper authentication. For instance, we saw twice authentication was required, but it wasn't truly validated. Microsoft has tons of documentation on setting up a secure channel. I know in auditing OEM WCF services, they properly secure authentication through tokens and keys. So it's possible, it's just that many developers don't do what it takes to securely authenticate connection to services. And lastly, try running as local service instead of local system. Local service has much fewer vulnerabilities or much fewer permissions than local system. There are a few ways to elevate from local service to local system, but this is a step forward if you don't require system privileges through your service. And in conclusion, so WCF endpoint abuse is very right vulnerability class. As far as I know, the only vulnerabilities that are public in regards to exploiting WCF endpoints are the one that I've reported, as well as those that are based on other vulnerabilities that I've reported, such as those found in VPN services. It's easy to analyze. You don't have to reverse engineer any assembly. You can just decompile it, look at the managed code, and understand what's going on. It's easy to exploit. There's no memory corruption. It's all like logic vulnerabilities that you're exploiting. So it's very simple for, even if you're new to attacking software, for you to pick up and take away some vulnerabilities with. And I advise you guys to hunt for more WCF endpoint abuse vulnerabilities. Any questions? I probably couldn't understand you guys anyway. That concludes my talk, I suppose.